Collision avoidance has always been a central aspect of robotic motion planning. Traditionally, manipulator robots have been successfully deployed in production halls to assist with a variety of industrial processes. In these highly controlled and manually designed environments, potential collisions can often be reliably predicted and prevented. However, like many of the roboticists and researchers working on further enhancing the skill sets of robots, we envision a future where robots are no longer confined to industrial production halls, but are prevalent in our daily lives. To achieve this long-term vision, robots are required to move out of controlled environments and into much more messy, unpredictable, and fast-changing territories. This transition bears many challenges. Cluttered environments and tight spaces where many potential collisions can occur are typically burdened with a great computational load. Furthermore, where human collaborators are involved, robots need to plan ahead while treating the humans as unpredictable, moving obstacles. In short, the increasing complexity of tasks that robots are expected to perform requires an equal increase in the efficiency of motion planning algorithms. In this work, we are working towards this grand challenge. Our goal in this paper is to derive a simple yet robust and customizable approach for collision-avoiding motion planning. To this end, we formulate robotic motion planning as a constrained trajectory optimization problem. The optimization variable x is the stacked states of the robot for the entire time-discretized trajectory. We model the robot using its kinematic information, where the robot state consists of its joint angles. The objective is the sum of several terms with the purpose to promote smooth motions, set motion targets, and enforce the robot's physical limits by adding soft penalties. Collision avoidance is integrated into the optimization in form of inequality constraints. We follow a common practice to avoid collisions by utilizing distance functions, which are used to penalize proximity of the robot to itself as well as to obstacles. Furthermore, like many previously derived approaches, we simplified the required distance computations by approximating the complex geometry of robots and obstacles by using simpler shapes. In this work, we run experiments with different collision primitives such as spheres, capsules, rectangles, and boxes. The drawback when using different primitive shapes is that it typically requires specialized code that computes distances for every type of primitive pair, which can be very cumbersome to maintain. In addition, some of the computations involved are known to be numerically sensitive, which can cause numerical issues throughout the optimization process, especially when gradient-based methods are used. These issues can lead to problems in convergence as well as constraint satisfaction. We tackle these problems in our approach as follows. First, we introduce a straightforward, unified parameterization of the different collision primitives using the parameters t. For the specifics, we would like to refer you to the paper. Second, we formulate the distance computation as a low-level, differentiable optimization problem. This allows us to explicitly handle numerical issues for all primitive pairs by adding a simple regularization term. Additionally, we introduce soft constraints on t by using barrier functions s. We then solve the resulting low-level minimization problem for each primitive pair iteratively using Newton's method. An implementation written in C++ can be found on GitHub. To solve the high-level trajectory optimization problem, we first convert the collision avoidance constraints into soft constraints by using the same barrier functions as before. This lets us solve the resulting unconstrained optimization problem by using Newton's method again. To this end, we show in the paper how to take derivatives of the distance computation by leveraging sensitivity analysis. We demonstrate that this approach generates smooth and collision-free robotic motions on a variety of simulated and real-world experiments for different robotic platforms. One of these experiments is this interactive example where two users are trying to poke the robot from both sides using sticks that are tracked by a motion capture system. Here, our motion planning method is run in a receding horizon fashion. Our experiments also include the planning of nominal trajectories. In this example, the robot is tasked with performing a handover through a narrow gap. The package as well as the wall can be modeled using the same collision primitives and formulation that is used to avoid self-collision. After pre-planning the trajectory in simulation, the resulting motion can seamlessly be transferred to the physical robot for validation. We currently do this in an open-loop manner. We also ran experiments for multi-robot scenarios. To this end, we include the motion trajectory for each robot into our optimization framework. Then, the same formulation to avoid self-collision and obstacles also allows the robots to avoid colliding with each other. More experiments and results can be found in the accompanying video of the paper. We would also like to encourage you to look at the discussion section of the paper to learn more about the limitations and the future work. To summarize, our approach provides a unified, straightforward framework that can be applied to various collision primitives and safely handles numerical issues that can arise when computing distances and its derivatives. Therefore, our distance computation scheme can seamlessly be integrated into path planners that profit from these properties. Thank you very much for your attention.